Mr. Massey.
Okay, just to give you a quick outline of what we're going to be going over. We're going to be going over the problem statement, introduction and background, functions and constraints, detail of design, analysis, and testing plan. Okay, so currently the BAJA SAE team is designing an off-road vehicle with the design requirements of having a maximum speed of 31 miles per hour, 0 to 20 miles per hour under 3.5 seconds, and capable of reaching the top speed in under 5 seconds. However, the current Briggs & Stratton 10 horsepower motor, along with the continuously variable transmission, do not provide the proper torque or angular velocity necessary to meet these design requirements. So, in order to fix this, we have designed a gearbox with a proper gear ratio to meet these requirements. Along with that, we've also made the gearbox. We also give the gearbox the ability to shift into reverse whenever the driver needs it. And for
okay, so I'll go over a little background of what the vehicle needs to actually do. So the competition includes like over 100 competing teams. So there's 3 competitions total. And then all these vehicles are student built and student designed. And they all compete in static and dynamic events, static which consists of a cost and a design report, and then a sales and design presentation. And then they compete in dynamic events of acceleration, hill climb, maneuverability, rock crawl, and then it culminates in a 4-hour endurance race to really test out the car. So for the requirements of the gearbox, it needs to work with a continuously variable transmission. And it has to have a gear reduction to transmit the necessary torque and power requirements to the output and drive axles, and include that reverse drive for those sticky situations.
All right, I'm going to talk about the function. The function of the gearbox is to be a gear reduction, which means that it will reduce the angular velocity coming from the motor, and also increase the torque to deliver the necessary torque to the drive axles. It will also serve as the power transmission. And so you can see the power flow coming from the motor. It will go through the CVT, be transmitted through the CVT, and then into the gearbox and through the gearbox and out the drive axle. The constraints of our project, a Briggs & Stratton Model 20 Intech motor has been provided to the team. It will be limited to 3,800 RPM for the competition. It puts out a maximum of 14.5 pound-feet of torque, and it's rated at 10 horsepower. The team, the BAJA, Sac-8 BAJA team also retains a Gauge Engineering GX8 Dominator CVT. The CVT essentially functions like a multi-speed gearbox. It varies the gear ratio from an initial ratio of 3.83 to 1 to a final ratio of 0.8 to 1. Jesse already mentioned the performance requirements, but an additional one is 350 pound-feet of torque at the driven wheels. The maximum dimensions of the gearbox need to be less than 17-inch by 10-inch by 7-inch, and our maximum budget is $2,100. And I will pass to you, Justin.
Alright, so for our design, here's our gearbox, and it's going to have a dog punch with a single bore drive, have a gear ratio of 8.48 to 1 with reverse. And our dog punch is basically this gear right here that engages this gear either forward or reverse with its dog teeth that go in. And for it to shift over from forward to reverse, we have the shifting mechanism that will allow the dog clutch to shift back and forth. And I'll hand it over to Nick.
So in order to determine the maximum velocity, we compared the power of the engine, which is actually 8.5 horsepower realistically, to the aerodynamic drag forces and the rolling resistance. As the velocity increases, the aerodynamic force increases quite a bit, and the rolling resistance increases a little bit less. when you take into account the inefficiencies of the various components of the powertrain and set them all equal in an equation, we find that 38.5 miles per hour is the maximum velocity with this estimate. However, we don't actually need to get 38.5 miles per hour, and the torque would suffer for that. So we actually went with about 8.5 miles per hour, which is within this range that the top equation demonstrates is required in order to get that velocity.
That's a big file.
That is 8.5 gear reduction ratio, the CVT's contribution to the gear reduction, the engine's output RPM, and the circumference of the wheels all give the engine speed based off those gear reduction ratios. Also, there's just a simple relationship between the torque and the angular velocity between maiden gears based on their teeth, number of teeth.
Okay. In order to ensure that we pick the right gears for our application, we use the stress equations provided by the American Gear Manufacturing Association. The primary failure modes we looked at were bending fatigue and surface fatigue. The first equation you can see is the bending stresses that our gears will be experiencing. The second equation is our bending strength. So this equation takes into account the amount of cycles we want these gears to go through, and gives us basically the maximum stress that they could handle before fracturing. And same thing goes for the contact stresses. So once we have the bending strength and the bending stress, we will compare one together and get a factor of safety. Our factors of safety were all well above 1, and max bending stresses never exceeded the yield strength of our gears, showing us that the gears that we chose were actually going to last for the year that we want them to last for.
Okay, we also had to take into account the deflections of the shafts to make sure that the gears made together properly. So the most complicated one was the input shaft, because the CVT actually puts a force on the overhung end of the shaft. It will be supported by self-aligning bearings, so we could model it as being on simple supports but overhung at the one end. We needed to make sure that the maximum deflection was less than 1,000th of an inch, and we used singularity functions to model the loading and then develop this deflection equation for at the gear, which is where we are interested in how far the shaft will deflect, and it was below the threshold. The other shafts were all modeled as simply supported, and were also well below the threshold.
So on the outside, you can see the 4 shafts that we are using in the gearbox. The idler shaft on the top right, the idler shaft on the top right is only going to be used when we use reverse, and so we considered it to be in static fatigue. The other shafts are all going to experience millions of cycles based on 15 hours runtime for testing, 3,400 RPMs for the engine, and so the fatigue stress that we use in this calculation is 2 million for the input shaft, and then it goes down from there as the torque increases and the RPMs decrease. The general shaft design equation also takes into account stress concentration factors for the end mill keyways that we'll be using to transmit the power between the gears and the shafts themselves.
Right, for the keys and bolts, the equation was used for shear stress is equal to force over the cross-sectional area. And it was found that for a 3/16 inch keyway, the shear stress was 3,500 psi, which is under the yield strength of the material. And for the bolts, the shear stress that it experienced was 2100 psi, and it was also well under the yield strength of its material.
Okay, so you used FEA for the more complex components because they have a much more complex geometry as well as unknown safety factors or unknown stress concentration factors. Also, for the case, it's a multiple part assembly, so it was ideal to use FEA instead of hand calculations. And for that, you get the largest displacement of about 1.9 10,000ths of an inch, and then the largest stress is about 1.14 KSI. And that leaves us with a safety factor of 35.1, so this is quite a robust design, and will be able to handle any additional impact loads this may receive, especially during an open wheel race. And then for the dog clutch, we did that analysis too for the same reasoning. For that, we get the largest displacement of about 1.6 10,000ths of an inch, and then the largest stress, which is the most important here, is 26.4 KSI, and that leaves us with a factor of safety about 2.6. So it'll be able to withstand any impact loads from shifting and not be able to get it in, and it'll be able to withstand any shocks from jumps and things like that. So, in order to test all this out, I'll send it to Justin with the test plan for the gearbox.
So we have 4 different tests that we will perform. First is the bending test to see that the deflections are less than 1/1000th of an inch at the gears. The next will be a hardness test. We're going to do a Bernal hardness for the gears that will heat treat and the shafts that will carburize. And we have an input-output loss. We'll check to see for the velocity that it's going to be at 35 miles per hour, the torque at 350 foot-pounds, and the power at 8.5 horsepower. And then for the shifting mechanism, we're just going to do a test trial to see if it's actually shifting properly. And for our fabrication, we're going to do all our work at the CSUS machine shop. We're going to use the lathe, mill, and CNC. We're going to carburize also on campus. And for our schedule, it's at the bottom. It shows our manufacturing timeline and our testing timeline. Thank you for your time. Do you have any questions?
Okay, thank our speakers.